observed and simulated data Look, this is not the only way to calibrate a model. This is the most frequently applied. So basically, and this is the ideal situation. It's ideal because you conceive a model and the model simulates a variable. And what you want is that the model is representative, is reliable. So the best way to check model reliability is to compare with observations. So this is the ideal target. Basically, I compare the model with the observations, and I estimate the parameters by optimizing the model performances in reproducing these observations. So this is the ideal situation. And this is, as I said, what happens in 95% of the cases. But in some cases, we don't have the observations. So there are alternative ways of calibrating models. And alternative ways, for instance, by guess. For instance, I told you that K may be related to the time of concentration. So you may apply a formula for computing the time of concentration, an empirical formula, and then assume that K is equal to the time of concentration. In this way, it's a form of calibration that you make. And it's basically empirical, it's a guess. Or you may also look at the catchment, and basing on your experience or knowledge of the catchment, you may say, here, more or less, the time of concentration is 4 hours. And so you get a K value of about 4 hours. So it's not the only way to calibrate a model, this one, but let me concentrate on this, because this is what we will try to apply. And as I said, it's a very frequent situation. When you can, you should always calibrate a model by comparing observed and simulated data. Okay, so if we focus on this situation, there is a first solution, which is trial and error. So, let me make an example. Suppose that you have an observed hydrograph, QT versus T, and the observed hydrograph, let's suppose that looks like this. And then you apply a linear reservoir model, and you take a trial value for K. So you get your trial value, and what you get is something like this, for instance. So you see that the peak is anticipated, and this is K1. You see that the peak is anticipated. The flood volume should remain the same. Remember that the area below the hydrograph is the flood volume, because the hydrograph is river flow QT. The area below the hydrograph is the integral of the river flow QT. The river flow, what is water volume per unit time. If you compute the integral of river flow, you get the flood volume. So the flood volume should remain the same, because the mass balance equation applies even if K is wrong. But if you anticipate the peak, then you get an higher value for the peak. Of course, because if you compress the hydrograph, then the peak, and the volume is unchanged, the peak goes up. So in this case, you see that the simulation is not fine. What would you conclude? That you need an higher K value, because you need to make the responses lower. So you take another K value, and you may get something like this. Okay, this is K2. K2 is larger than K1. But in this case, you see that you got to the opposite situation, where K is too large. And so you may take a K3, which is something like this. I use a dashed line. And this is K3. And then you could be happy. And look, I didn't I didn't depict here a perfect simulation, because the simulation will never be perfect. You have to, at a certain point, to judge whether or not you are happy. Why the simulation is not perfect? Because the model is based on some assumptions which are not verified. The linearity is the most important. So you will never get a perfect simulation from an hydrological model. Never. There is always uncertainty. This you have to have clear in mind this. So at a certain stage, with the trial and error procedure, you could make the calibration. And you will see that it's very easy to make a trial and error procedure, because with the computing means that we have today, it's very fast to run a simulation with the linear reservoir. It takes less than 1 second. So you may just write a R routine, you will see tomorrow, we will see tomorrow, and then you change the K value several times. And this is something that can be certainly done. At the beginning of our history of hydrologists, we always use the trial and error, because you know, it was more immediate, and we were dealing with simple models. So this was really doable. And the trial and error procedure has a great advantage. It allows you to check what's going on. It allows you to use your reasoning. So in this case, we made some reasoning. We looked at the hydrograph and we made some reasoning. And we made several simulations. It was not an automatic procedure. So basically, this calibration was done by us, not by the PC. The PC is just a computational tool in this case. And you know, this means that you gain a very good knowledge of model performances, of the quality of the hydrograph, etc. But the trial and error procedure has some disadvantages, and the disadvantage is that in the case where you have more than one parameter, think of a model that may have 5 parameters. It's not easy to make these trials, because if you have just one, you have only 2 choices, increase or decrease. If you have 2, you have already 4 choices, increase and decrease, decrease and decrease, increase and decrease, increase and decrease. So it's already complicated. If you have 5, think at the possibility, and you have tens of possibilities, and therefore, you know, it becomes very complicated. And at a certain point, it's difficult for you to follow what you have done already, what remains to try, and you may miss some possible solutions. So people started at the beginning of the 90s with the availability of PCs to think at the possibility of automatizing this procedure. So think at the possibility of devising algorithm, making the trial for ourselves, which is very useful indeed. And people did a lot of progresses, and today in every package, any statistical package, but also in Excel, is equipped with optimization algorithms, which means that they look at the various combination of parameters for you and identify the best one, which is very handy, and made the calibration faster and faster and faster. So basically, there is one thing that these algorithms need. They need a criteria to judge whether the PC, namely you, are happy with the simulation. Because they look for millions of trials, millions, because you know these parameters are real variables in most of the cases, and therefore you have potentially millions of combinations, and they look for the best one, but at a certain stage they have to stop. And they need a criteria for deciding when to stop, but also a criteria for deciding if a solution is better than another one. So our criteria is a visual comparison. In the trial and error procedure, it's a visual comparison. If we make this procedure automatic, we need a criteria, to introduce a criteria which is called objective function. So basically, what the computer does is to compute the objective function for millions of parameter combinations and to identify the best value, better, to identify the parameter combination that provides the best objective function. And this is a bit of a complication because we need to translate into a number through a function our happiness about the simulation. This is the first complication. And there is, and we will discuss about some objective functions in the next hour. And there is a second disadvantage, that you lose the control. So basically, you run the algorithm, the PC, and then you go out and get a coffee and have fun, and then you get back and you have the result. But you didn't follow the procedure. So basically, if this is an advantage on one hand, because you can use the time to do something else, on the other hand, there is the risk that you lose the perception of how the model is working. So basically, the technician needs, every time that an automatic procedure is run, you need to take your time to check the results with care, because there is the risk that you take for good everything the computer delivers to you, which is a big risk, because you are an engineer and the mistakes are possible even for the person, and for the computer it's even riskier. Okay, it's more risky. We stop 15 minutes.